It only took like 3 PhDs to figure this out, guys. So we're good. All right, let's go. All right, it's my pleasure to announce Dr. Kayla Iacovino, who is an undergrad at ASU and did high pressure research in the original Depths of the Earth High Pressure Lab. She earned her PhD from the University of Cambridge and went on to postdocs at USGS Menlo Park and here in the EPIC Lab. Currently, she works at Johnson Space Center for NASA via Amentum, formerly Jacobs. Besides Antarctica, she has conducted fieldwork in places like, consult my list, Costa Rica, Nicaragua, DR Congo, and North Korea. She has been featured in science documentaries, including Breakthroughs, Portraits of Women in Science, Expedition Volcano, and Pompeii Secrets of the Dead, and has made many appearances on news programs such as NPR Science Friday. She has been recognized with many honors, but I'm sure none so coveted as, for those of you who remember when we gave out awards at the CC picnic, for outstanding CC postdoc.
No, it was the
least forgotten postdoc. Yeah. So without further ado, Dr. Kayla Iacovino.
Thank you so much, Kara, for that introduction. Thanks everyone for being here, and thanks ASU for hosting me. It's great to be home. Did my undergrad here and a postdoc here at Casey Hill, and grew up in Scottsdale. So not that I recognize Tempe anymore, but it's nice to be back. And thank you for your patience as we got this worked out. I am going to be talking to you today about kind of a high-level overview of some things I've been thinking about recently, looking at how we can take the knowledge that we have within academia and kind of break it out of that ivory tower and use it not only to make us do better science, but to help us actually apply it to the things that we really want to be applying it to. And so, like right out of the gate, I'm going to throw a little bit of shade. So I'm an experimental petrologist, but I think this applies to most people in this room. And if it's not hazards, insert your favorite thing there, search for life, water on Mars. So we write these proposals where, we say, okay, this is important because hazards. I'm a volcanologist, so hazards, right? And then we have this method section where it's like super detailed of how we're going to measure the partitioning of tantalum between clinopyroxene and magma. And then we're like, and then hazards, right? So it's kind of this situation where, we don't know, we're missing a link here, right? Or here. So then the question becomes, how do we draw the rest of the owl? How do we fill that gap? And then something I've been thinking about, I've been reading science philosophy, thinking about how breakthroughs in science are made. And Thomas Kuhn is a science philosopher who wrote in the 1970s a lot about how science progresses. And one of the things he defines is what he calls paradigm shifts. So paradigm shifts in between normal science. And so you can think of normal science as the majority of what we do. We write a research grant, we work in the lab, we get results, we present them, and science progresses bit by bit. And it's hard, thankless sometimes work. And then every once in a while, something big comes about. And so we build our model of the universe more and more until we get to a point where there are more questions than answers. So if we stick with the current model we have, our new ideas, the new data coming out, do a poorer and poorer job of that. They challenge that model, and then a paradigm shift happens. So a good example of this in geology is plate tectonics. We had all these ideas about how the Earth works under the idea that the plates were stagnant. And there were more and more observations that didn't work if that were true. And a bunch of people got together and said, hey, what if the plates move around? And we shifted the way we thought about the Earth. And then that enabled a whole new level of understanding. And so I'm interested in how do we enable that? How do we make that happen? And it can happen through technological advancements, through breakthrough ideas. But if we're at the precipice of something like that, how do we turn that knob? And so first, I know this is a general audience. In fact, I'm curious to poll the audience, like how many people here don't do what they would consider geology? How many people don't do like physical science? Okay, but what do you do? Education research. Okay, awesome. Very related, but yeah. So I think, and there's probably engineers in here. I see computer scientists in here. So I'm going to challenge you throughout this talk to think about what you do and something as you maybe didn't come to a talk about volcanic gases thinking, oh, I'm going to get so much like from her topic, but try to think about like something that I say that's, oh, we think about something similar in my line of work, because I find like I learn a lot of people about things that I do from people looking at completely different things, because we all use a lot of the same tools. So introduction to volcanic gases. This is, oh, here comes the getting more sciencey plots now. So this is just kind of a very big overview of some rocks. So we have some magmas. We have Kilauea, Fuego, Fogo, and then this andesite chondrite. So representing things really in the early solar system. And the gas, the volatiles or the gases, they're the things that are have the propensity to dissolve into a gas. Meaning in magmas, it's going to be largely hydrogen, carbon, and sulfur, the three main components. There are some others. And this is just kind of showing you how much of different magmas they can take up. So this is in molar percent, and this is by element. So you know, iron, magnesium, and like silicon, aluminum. And in things like Fuego and Fogo, you have really, really water-rich or hydrogen-rich systems. And then andesite chondrites, you get weird stuff going on with sulfur and carbon, and different chemistry happens. And these are the things that turn into volcanic gases at the surface. So that's what I'm going to be focusing on really, is that volcanic gas that volcanoes are pumping out. So non-exhaustive list of why my topic is important, right? And I see that I feel like hydrogen, let's say, or volatiles in general are relevant to almost every physical science discipline, because they're the mechanism by which we move stuff between interiors and exteriors of planets. Volatiles are mobile, so they can take stuff with them. They can concentrate things. They create porphyry deposits. Here in Arizona, we have a lot of copper porphyry mines, and those are from magmatic volatiles. There's going to be a bonus question at the end of this talk. So think about what do you think magmatic gases could possibly have to do with your smartphone, and what could they have possibly to do with recent world news? So how do we study magmatic volatiles? I'm going to take you on a little bit of a history lesson here about volatiles in magmas, and going from the gas sampling. Sorry, that's kind of low on the screen there. Gas sampling, so this is how we measure things, how we experimentally work with those things in the lab, how we create models, and then like how we use technology. And yes, I knew this was going to be a very contentious history because I had to highlight certain people's work. So just disclaimer, if I left your work out, I claim no responsibility for that. So in the beginning, there was the Hawaiian Volcano Observatory. Again, I'm sorry this is so low, but that's the Hawaiian Volcano Observatory gas sampling. These are in like the early 1900s, black and white photos of people, like women in dresses, like gowns, like hunched over a lava, measuring the gases that came out of it. And then we had people like Bowen and Tuttle, who two of you in the room will know like how important they were to understanding petrology. Tom is like, more people should know about this than too. The Bowen's reaction series, all these things. So they were the first people to kind of invent this idea of expat as we know it today, experimental petrology. And I've highlighted, gone back through and realized a bunch of this stuff happened here at ASU. So I put a little star if I thought it was related enough to ASU. So in gas sampling, we moved to doing, this is like spectrometry measurements. We started coupling like physical samples of crystals and glass with the gas measurements. And then we started modeling things. We started modeling just water, then water and CO2. That was by John Holloway, who was here at ASU. And note that this all happened before the invention of the World Wide Web. So a little perspective on the timeline there. Moving into the next century, we had more and more progression of experiments. So we had a higher pressure, and then we had more, again, this is the experiments coupled with the actual measurements from the rock. We had more kinds of spectroscopic analysis of the gases, and then different types of magmas that we could model going forward. Meanwhile, in the infotech sector, like Python became a thing, open source became a thing, and we were like moving to this sort of web 1.0, web 2.0, like everything is going to be open and free vision. And you'll notice what I kind of identified as what I would say are paradigm shifts, at least within our field here. So we started doing this in general. We started adding more, we had higher pressure, and now we're getting into more and more compositional space. So we added halogens and sulfur. This is a huge one. We added sulfur. And we started having these tools. This is an Excel spreadsheet that's still very heavily cited today. Halogen models has had sulfur in it. And then meanwhile, we have scientific computing really taking off. So we had NumPy, SciPy, and then when GitHub first came around. And then sort of kept going in that way. So now we're combining more and more data sets. We have automatic and telemeter data. And this is a thing I'm really going to talk about today is this idea of general thermodynamic models. So rather than doing an experiment on kilo A basalt and coming up with a model for that, can we combine all these data and make like a general model of magmas? So the question, right, is what's next? And I would argue that we're on the precipice of one of these paradigm shifts if we choose to enable it. And so again, this is kind of, Bowen being more and more high pressure, come up with the empirical models, coming up with general models. And where do we go from here? How can we accelerate that? So there's two ways you can shrink that I see, right? You can shrink the x-axis. So you can do a lot of work in a little bit of time. Say a huge grant and you could enable like a ton of science all at once, more normal science. Or you could stretch that y-axis. You could use something like a technological advancement to create a new foundation upon which to do normal science. And that's what I would see really as a paradigm shift. So sort of another way of showing this, and I'm sorry, this sort of does get a bit into the weeds, but again, it follows this idea of specific models for specific types of magmas into, these are some generalized models that have come out. And then right now this is where we are now, is we have a couple of these generalized tools, but what we're missing is the interoperability of these tools. And here's why that's important. So a few of us, 8 of us, right, have gotten together. These are people who use or have created models to understand how volatiles work in magmas, how they come out of a gas, how they drive explosive eruptions in volcanoes. And we're all creating these new models. We're all using some of the same tools within our models. And we're like, we should get together and understand why our models aren't producing the same results. We're taking different approaches to these things, but really what's driving this? So right now, if you want to go and understand, measure volcanic gas and understand where it came from, that's not as easy as picking, the model and running it. You have to answer a lot of questions for yourself. So, first of all, one we want to interrogate is, why do our models disagree? How do they disagree? And when do they disagree? And what circumstances? But for a user of the model, they say, well, which model should I use? Tailored to my system? Do I want a more general one? What if I have new data and I think it could, the experimentalist has new data and they want to add it to the existing model and make that model better? And then, of course, accessibility, right? A really important part of fair data. Which model can I figure out how to install and use? And I don't even need to ask people to raise their hands if they've ever gone to install something and thought, yeah, no, that's too much work. I already don't understand it. So we focused on this question: why do models disagree, and how and when? Right. So we got together, had a bunch of meetings to decide which calculations would we perform that could kind of encompass our models best. And so we chose what's called a degassing path. So this is from one of our in the group, Ari Hughes. Read the docs page, just showing a nice like magma chamber, and the volatile is going to be dissolving on the way up. And this is how we're going to be looking at some plots coming up here. So this is so we have pressure on the x-axis, and then whatever dependent variable we're interested in on the y. So typically we're looking at how much H2O, CO2, sulfur started in the melt. It all started not as gas, and then we let that gas come out into bubbles, and we do that as we come down in pressure. So as we go up the magma chamber, we're going to the left on these graphs. So we'll start somewhere up here, And as we change, go up it, down in pressure, up in the conduit, we'll start to take more and more of that water out of the magma and put it into a gas until we reach the surface, right? So this magma chamber down to the surface. We felt like this is a great way to run this full path because you're doing this stepwise. You start calculating this point and then you stepwise calculate things all the way down. So it allows us to look at all the different parts of our different modeling tools kind of in one. And so we chose to do this on 4 different basalts that varied in these different chemical spaces. So we have a mid-ocean ridge basalt. We have, so this is volatile pore, it doesn't have a lot of volatiles. We have Kilauea, also volatile pore, but has a different major element chemistry. Fogo, very volatile rich. And then Fuego, which is also very volatile rich, and then again, a different chemistry. And so this is just sort of the space of where these basalts exist in terms of water, CO2, sulfur, temperature, estimated temperature space, and then this fun term, which is oxygen fugacity. And I'm going to talk about that in a bit. And just think about it basically as sort of the oxidation state of the magma. How much oxygen is there around to react? And this affects what iron does, because iron can take more oxygen or not. So this affects a lot of different things about the chemistry of the magma. So it becomes really important, especially for sulfur. I'm going to share the results with you first and show you how we came to these conclusions. So these are why our models disagree and how and when. First of all, this H2O and CO2 solubility models are I would say, maybe not the simplest, but sort of as you saw in the history, the oldest pieces in terms of modeling that we have. And so those set the initial conditions for the run. So it turns out those are overly important in our modeling. Typos and bugs, we hate to admit it, but all of us have published papers with typos in them or turned in a paper with typos in them, and they are there no matter how hard we try. And then this one is probably my favorite, surprisingly simple assumptions. And then, of course, as the degassing progresses, as you're going stepwise through this process to eruption, these differences stack and build upon each other, kind of like a snowball effect. So let's start with the first one. How do we get our initial conditions, and why is that so important? So this is from a paper with myself led by Penny Weiser. And again, we're looking at, this is pressure from deep to shallow. And so this would be how much water is in our magma dissolved and how much CO2 is dissolved. And these are 3 different models just for water and CO2. And you can see at 6 weight percent H2O in our starting magma, you could calculate a pressure anywhere from about 1.8 to 3.5 thousand bars. So that's almost 2x disagreement. So we're starting at 2 completely different pressures from our initial condition. And the CO2 is even worse. It can be up in order of magnitude different if you just use the CO2. So if you have 2.2 weight percent CO2, you could be at this whole range of half of 1,000 bars to over 4,000. So that's already not great. So depending on which model, H2O CO2 model is underlying the rest of your code, your results will be very different. And that also is why I'm going to show you these plots in a slightly different way from now on. So this is just a look at that saturation pressure calculated for each of our basalts. And each one of these points represents one of the models one of the tools that we tested. And so these are all the people I showed their pictures of. Each one of them owns one of these. And we all ran our calculations. And there's a huge disagreement here. This goes from 1,000 to 7,000. And then for Fuego, one of our models is off the scale, 10,000 bars. So because of that, I would be showing you a bunch of plots like this, where it's sort of hard to compare the trends between them. So like, okay, we know that makes a big difference. We're going to sort of ignore this for now. And so the following plots, I've normalized pressure, basically. So just like pressure on a scale from 0 to 1, start to finish. And that way you can see this is the same data. So you can just see it's like, okay, we can see that those agree, at least in terms of trend. So we can remove that initial condition problem. And when we do that, we see that for H2O and CO2, we feel okay about it because the trends are okay. They're not like alarming. Something weird happened here, and we have to ask Echo about what happened to your model there. But in general, Fuego is one of the more volatile rich ones. It's a little bit different. But in general, we're like, okay, this isn't too bad. So then it's this treatment of sulfur. So sulfur is not fun for experimentalists because it bonds with everything, and just corrodes our experimental equipment, and is multivalent. So it can be sulfur in 2- form, and it can be +6. That means it has the capacity to move eight different sort of electron states, right, of sulfur. It means it bonds with different things, and that ends up changing how much sulfur a magma can actually hold in it. So the way we model the degassing path, whether you get more or less out of the top of your volcano, really matters. And so it's always more complicated. And really the thing about the models, the tools that we're testing, is that a lot of them are their own in-house sulfur model on top of a pre-existing H2CO model. So unsurprisingly, perhaps, we find that sulfur becomes the most complicated thing. Now, Kilauea doesn't have as much, which is why it doesn't look as bad. Same with Morb, but the Fuego in particular and the Fogot is that like this is when we get concerned. And so like as someone who's creating these models, I feel like I at least have the expertise to tell you like, this is okay, this is concerning, this is concern face. And this sort of, I don't want to go into too much detail on this, but basically suffice it to say that what this has already shown us here is that if we kind of strip away some of the complexities, now we can start to finally be like, okay, now we see why our different treatment of sulfur is creating different results. But for other reasons, we haven't even gotten to that stage yet because we found other really, this is my favorite part. It's like, it's crazy what we didn't even realize what assumptions we were making creating these models, because we're the ones who created these models. We got together, and just for context, it took us maybe 6 months to be certain that we were all even modeling the same thing. So the fact whether our inputs were the same thing, because they might use, this unit, and we might use a different unit, and we converted between the units, but they converted it in a different way than I converted it. So is it the same thing? It took us 6 months to figure that out. And so like, if we can't figure that out, how do we expect anyone else in our field to figure it out, let alone someone not in our field, let alone the observatories who are measuring the gases use these things at all? And so it's both this, so major element normalization is probably my favorite one because it's the one it's like you least expect it. So when we have a geochemical composition of something, it's in terms of percent, right? You have percent sulfur, some percent sodium, adds up to 100%. Sometimes because of error, it doesn't. So you might have something where the total is 96%. And typically what we do is we normalize it. So we just sort of raise everything up to 100% and re-proportion it out. But it turns out there are 3 ways to do that. And we didn't really think about the fact that we're all doing it differently. So if you have a magma with, actually, I'm going to go back to this other slide that I showed earlier. So if you have, go back to this example, right? If you have your Fuego volcano and you have this much non-volatile stuff, so this much, rock forming elements, let's say, you could choose to take just this part, normalize it to 100%, and then your volatiles are like extra. So your total is now like 103%. Okay, you could normalize the whole thing, just reproportion, stretch everything out to 100%. Or you could say, I'm going to normalize the whole thing to 100%, but I'm going to hold these values constant because of the way in which I measured it. So I have really good confidence in this number. So I'm going to kind of say, this is, what are we at? 25 mole percent. We're going to hold that there and then stretch everything else out so that the total is 100%. And it seems like it should just be a few percent difference, but it turns out it changes the results we get by a lot. So that was also concerning. But it's like, we need to we're realizing that we just need to get together and talk about what we're actually doing before we can even understand what our own models are doing. And here's another example, going back to everyone's favorite topic of redox and oxygen gasing. So this is, again, that measure of how much oxygen is available in the system to react with stuff. And it's complicated because we use so many different terms to talk about oxygen fugacity. A lot of you probably think about pH. A lot of you probably think about redox. You might think of multivalent elements, iron 2+3+. You might think of this weird esoteric concept called fugacity, partial pressure of oxygen. They're all the same thing, kind of, but expressed in different ways. And so we chose inputs for that value, oxygen, of two different types. We chose one where we expressed it in terms of the valence of iron, so how much 3+ to 2+ is in the system. And we had one where we expressed it in this funny thing, which is this just sort of esoteric term, oxygen fugacity. And it turns out that there are like a lot of models to convert between. Now, some people's models took this value like that, 3+ to 2+ iron. Some people's models took this value like that. Someone took it in a completely different way as an input. So we all had to do conversions and figure out what the actual value was, which when you convert from one thing to the other, they don't always agree. And so these are the input values for each volcano. And so what I'm expressing here is, again, the degassing path from high pressure to low pressure, and then that oxygen value on the y-axis. And this is in terms of oxygen fugacity. So when we input something as oxygen fugacity, and then we model the result in terms of oxygen fugacity, it's like, okay, this is concerning. This is okay. And then for when we input the value as Fe3 plus Fe total, and then we plot it as this type of value, it kind of like, there's no understandable way to explain why it's going to be like not converging for any of those all the way down the pressure line. And the opposite happens when you do it the other way. So in this case, like these three look okay because we input iron valence, we got out iron valence. But if we input oxygen fugacity and get out iron valence, now this looks bad. So that leads me to the final thing of these minor differences stack, you know, as these progress. Like this clear here, right? It's like, oh, okay, this is weird. This is okay, and then wow, this is not what's happening, right? So things are just snowball effect. And just to show you, now this plot, I probably would have shown, if I had a student that showed me this plot, I'd be like, do not show this plot. But I'm showing you this plot. So like the details aren't important, but I think you can tell if you're thinking like this plot is hard to understand, that's what I want you to get out of this plot. These are the different tools, tools that we were testing, our own tools. And these are different variables, right? We want to put into the model. And each square represents a different model to describe this term that's inside of our model. And some of them has multiple choices. So like sulfur X, you could choose either a pink one or the yellow one. This one you could choose the yellow one or the green one, but not the pink one. And so if my friend Echo, who wrote sulfur X, was running the pink one, but then Sunshine, who wrote Magic, was running the yellow one, like that, and then the whole space. So when we started looking at this, we were like, yeah, this is a problem. And here's my other favorite thing. So there's a star on this one. This goes back to the oxygen term. We're all using, except for Magic, he does his own thing. We're all using like this same Kress and Carmichael 1991 paper to do this conversion between these units. The star is because, oh yeah, that's Ari Hughes, who's written this model. He's like, oh, I'm also using that paper, but I'm using the equation that's in the appendix. And you guys are all using equation 7 from the main text. And we were like, first of all, Ari, why? But see, like that's something, like if you read her paper, would you know that? And I doubt many of you know that there are two equations, or have read Preston Carmichael 1991. So as someone outside the field, again, like much less hope to use this model the way that we intended it to be used. And so just another example of like combining all of these things. When you combine sulfur, which we know less about, and this oxygen term, just more of as well, still not okay, because this is the problem. But this is sort of all everything breaks loose. And this is what we want to be modeling in the end. This is what I want to be. This is a whole system with sulfur, water, carbon, oxygen content. And we've made a measurement of all these things at the surface, right? And if we want to understand where it's coming from, good luck. So with all of that said, what's the point of this, right? How could we build a new framework to enable discovery within our field as a tool for observatories, and even into policy making about volcanic hazards, about porphyry copper deposits, about the people who live on those lands, about Yellowstone and extremophile life, and all these things affected by magmatic processes. Well, like I mentioned earlier, interoperability is the thing we're really missing. And so it took us so long to do all of these model runs. So this is just stuff you've seen. This is the Fuego degassing curve for each of these components. And you can see it gets like crazier as you go. And it took, again, the fact that it took the individual people who created the models like a year of work to even just like run all these scenarios, because they couldn't talk to each other and we couldn't easily interrogate them. We all had to run them ourselves. They were on different platforms. But imagine if we had a centralized code framework that was more like an API, right? It had all of these models inside of them already, all of the Crescent, Carmichael, and all these things. And any tool anything you wanted to use it for, you could build a model. You could be our seventh person and build a seventh model. But if you used at least our underlying structure so that how am I normalizing performance? How am I converting these units? Then you could at least compare your results. Because right now, we can't even compare our results. And so volcanic gases are, in my opinion, this very important part of a volcanic story and very related to hazards. This is what a volcano observatory typically looks like. You have in Givu, this is Etna. This is their center in Rome. This is the USGS Alaska Volcano Observatory. And one thing they all have are these are live feeds of seismic data. And these are like near real time, telemetered straight from the volcano from seismometers. And that is the main data that's driving our predictions and our forecasts for what a volcano is going to do. And volcanic gases have been this thing that geochemists have been trying to figure out how to like use them as this tool for decades and decades before I ever started doing science, because they're a powerful descriptor of what's happening chemically in the system. This tells us magma is moving around somewhere, but it doesn't tell us with that there's a lot of gas that's going to come out of that, or a lot of other important things. And so it's because of this modeling problem, we know a lot about this stuff. We've been studying it. I showed you my timeline for decades, since the early 1900s, and we still don't have a good framework to model it in a way that's useful to anyone, ourselves, let alone anyone else. And so I'm kind of envisioning a world in which we have this central framework full of standards that we all agree on as a community. And you can imagine these also being alongside screens with near real-time telemetry data of gas chemistry, which those instruments exist. They're on the volcanoes. We're getting the data now. They don't do anything with them because it's such a high barrier to entry. Turn it into something useful. And so that's kind of what like I envision in terms of how we could actually put our work to use. And so kind of like this big overview goal, right, is there's a couple of different ways that we do science. And we want to keep doing it. We want to keep doing experiments. Sometimes I'll give it a talk to experimental audience and I'll imply that we should stop doing experiments because then they'll pay attention because they want to raise their hand and tell me why I'm wrong. And then explain like, no, you can keep doing experiments, but you're not using the ones that you already have. Let's stop and let's look back and let's what is the point? Why are we here, guys, right? So keep doing it, keep going onward and upward. We can also look, downward, back at our history, back at ourselves, and we can start to use these tools that exist to us that other fields are doing a much better job of utilizing to, not only understand the universe, but then to apply that in a way that helps make the world a better place. So I'm getting really philosophical on volcanic gases. Didn't expect. Cool. I'm glad I didn't ramble on too long because I have time for my bonus question. So what do magmatic gases have to do with your smartphone or recent world news? I kind of hinted at this a little bit. They have to do with a lot of surprising aspects of your life, and I couldn't quite decide which one to pick, but I did just pick one. But there are a lot of these stories I could have told. So I'm going to tell you a story in maps. So this is a map of Africa, and the colors here are very low in gray to very high in red of geothermal energy production. And so there's a citation here, so you can see hotspots. And unsurprisingly for some of you, this falls along the East African Rift Zone where Africa is tearing itself apart. And so we have a lot of geothermal energy coming up from the mantle as it upwells while the crust is being pulled apart. Now you can lay over that a map of active volcanoes. Again, probably unsurprisingly, they lay right along where those high geothermal areas are. This is Ethiopia and this Ethiopian Rift. And then I want to focus now on this country in the center called the Democratic Republic of Congo, where there's a bunch of volcanoes right here. And we can compare that with a zoomed in map of DR Congo and look at the number of mines that exist there. So this is a very ore-rich, mineral-rich country. It affects a lot about the lives of the people there. So these are gold, tin, and coltan. Now coltan is cobalt and tantalum. And it turns out that 73% of the world's cobalt comes from these mines in DR Congo. And every iPhone, it's actually my iPhone 6, but has about 6.6 grams of cobalt in it. It's about 5% of the phone in your pocket, plus the Androids too, has about 6 or 7 grams of cobalt in it. And where there is a bottleneck in the supply of something like that, there is conflict. And so coltan is a conflict mineral, much like gold in a lot of places in Africa or diamonds in South Africa. And this is a map showing basically United Nations analysis of that same region of Eastern DR Congo. And the red is where you have both gold mines. This is just for gold, but it applies to everything here, both gold mines and a high rate of violence. Yellow is no gold mines and no violence. The green and pink are sort of in between. But clearly where the mines exist, there's a high correlation between the mines and violence. And as the mines continue to proliferate, we add more mines, you see it not only affecting those regions, but the adjacent regions to these pink regions, with violence spreading into these areas. So again, yeah, just the comparison there, it's pretty hard to miss. And that, not only does that affect our lives, but obviously affects the lives of the people who live there. And so right now there's huge conflict going on in the city of Goma. It's a city of about 1 million people who live on the side of a very active volcano, and has been a complete rebel takeover of the eastern side of DR Congo. So not to be a downer, but it's one of these things that geology affects kind of everything. The fact that someone's life who's living in the DR Congo might be bad right now because Africa decided to start ripping apart hundreds of millions of years ago. And so that's kind of that's why these things are important. I think it's important for us to remember what are we doing here? Why do we do this? And if we don't take the opportunity to stop and think about how our work is being applied, what it's really doing. It's so easy to be in the churn and move on to the next publication because we need to get a job, we need to get tenure. And, you know, tenured are the privileged few who can have more opportunities to do things like this and stop and look around. You know, maybe we can do something important with that. And I just threw this in here because Kara mentioned it. If you thought that was interesting and it speaks to you at all, I recommend this, not just because I'm in it, but this is a documentary that we filmed in the DR Congo for the BBC. That's the lava lake. It's the like 300-meter wide lava lake in a volcano. And it talks a lot about this story and the people who live in the Congo, why the existence and the lives of the gorillas in the DR Congo are affected by the volcanism and all kinds of things. There's a PBS Nova version as well, but the BBC one is better. Watch the BBC one. Yeah, and that's, other than my extra slides that no one's gonna ask me about, that's it. So thank you very much for paying attention.
Thank you so much, Kayla, for a really great talk, something really different we don't get a chance to see here very often. Does anyone have questions for our speaker?
Even though I'm holding the microphone. Can you explain how cobalt relates to outgassing models?
Yeah, great question. Okay, so I didn't want to, add too much complexity to that, so I didn't get into it. But basically, like I said, these volatiles are really mobile things. And so things like cobalt will get concentrated in volatile phases or in fluid phases. And they're the things that sort of, like I said, they concentrate them. So you get zones of ore deposits from rocks that didn't, even gold, right, or coltan. You didn't have much of it in the rock, but it all got concentrated in one place, and that's how we get ores. And that's all about fluids, are doing like all of that work. And so the composition of the gas has a very big role on how much, say, cobalt gets incorporated into that fluid. Sulfur is really important because it bonds with a lot of metals. Gold, iron, cobalt, tantalum, all these things bind really well with sulfur. So it can pull them out of the magmas and help concentrate them. So understanding how we go from magma composition to ore deposits is really dependent on the composition of the gases and how easily they can move out of the magma.
Thank you.
So if even you as the model developers were surprised by all these interoperability and incomparability problems, do you have thoughts or advice for what the field as a whole and all the model users who aren't as sophisticated as you, like what's the future if the model developers are even,
Yes.
you know, so
Yes. Thank you for asking that question, so I can talk more about that. I think the answer is, and this is where we have to choose this as a community, because it takes a village, to do this. I think we need to choose to come together and create a set of standards, at least to start with. So we're not all speaking the same language. I think a lot of us in CC is very interdisciplinary. So I think a lot of you probably have encountered this, but within our own field, we're not either. And within the codes, we're not either. So we need to be able to speak, they're all written Python, except for one. All of these are in Python. We're just not using the same terms or the same normalization. So if we're trying to do this with this group, get together, create a set of standards, and then give advice to the community. And my advice would be, again, let's get together and agree on something. And then let's create sort of a modeling consortium or a group that other fields have something like this, where they are kind of the keepers of that community, those community decisions. And that way we can like allow everything to plug into one central thing. So some centralization, I think, is a good thing. And it also enables, if you have a centralized like piece where you're just like, okay, these are all defined here, 2 + 2 is 4. Then you can also build sort of shells on top of that. So you could build something for the student or the professor who doesn't want to learn or can't have time, whatever, to learn how to like code on that level. They just want to use the tool. Well, now you can very easily build a little thing to attach on top of that central sort of API central model. That's like just like a more simplified portal. You know, it's like a GUI on top of MS-DOS. You don't know how to use command line, but you can click a mouse. So it just enables those things to happen. And now we can not waste time. Like it could take a PhD, entire PhD worth of time to do a real comparison of this. But if we had a tool that could just make them all talk to each other, it would take a day. So that's where I think, if that answers your question, I think that's what we need to do. Did you have your hand up first? Or who's first?
Oh, there you are. Thank you. Hi, do you think we need a change in the culture of how we publish papers?
Absolutely.
Because there's this trend to, I mean, when I'm a modeler and I write all my assumptions down, I'm accused of being pedantic or writing too long a paper. And so they get buried and sometimes they're put in a supplementary material and it's all buried there and you can't even download the supplementary material when you download the paper, and it's annoying. And it feels like the journals are trying to make it seem as if this is all trivial and not worth knowing about. And it is central to making progress in the field.
Thank you for mentioning that. Yes, this is the other thing. One of the things we're going to recommend in this paper is that we need to start demanding as peer reviewers certain standards that we've never adopted. So it's 2025. And there are people publishing papers of a code they've built that don't publish the code. Like, that'd be like publishing a paper that says the answer to the universe is 42, but not how you got there. Like that, to me, that's like against the basic principles of science, which should be reproducibility. And I've been a reviewer on papers where they've said, here's this big data set. It's part of a bigger group, so we can't publish all the data right now because we need to publish it somewhere else. And I said, I'm sorry, I have to recommend rejection of the paper because I can't evaluate your claims if I can't see your data. They publish the paper, but because the journal is not going to solve this problem for us because they don't care. Elsevier does not care. So I think we need to that's another thing we need to come together and agree on. Like, what are our standards for level of publication? We need to push things like Zenodo is one tool for like sort of taking your code and archiving it in this static format and GitHub and all these things. It's all part of it. I think what we can do as scientists is be rigorous within the peer review process.
Hi, Kayla. Thanks. This is great work. I love it that you've done this comparison with your entire gang of
Thank you.
folks. The question I had for you is, which one do you think gives greater errors or discrepancies in the comparisons? The code, the physics behind the code, or the database? Because I feel like my community of planetary scientists, we make our own databases of it, right? So there's hundreds of people doing their own thing, the same thing over and over again. And I feel your pain of not having one common database, right? So I thought the terrestrial, folks are doing a better job, but looks like the databases are not there as well. So yeah, so the question is, which one, gives a greater error, you think? In
that's a good question. I mean, my first answer is it depends, right? So I think, correct me if I'm wrong, I think what you're asking is, do we have this database of underlying experiments? So we create like a regression or what have you of that, and we have an equation. So is the problem how we choose to form that equation, or is the problem that our databases that we're pulling from different data sets, right? So probably both. If you have a really big data set that encompasses a lot of the variables you care about, I would guess, this is a guess, I would guess that the formulation of the equation makes a much bigger difference. But then like answering the question of, do I have a big enough data set that covers all my variables is also like not easily answerable. But I think like they can both be answered in a similar way, because the way we treat databases and the way we treat code are both behind where they should be. So this idea of an API, so if people use like GeoRock or the EarthChem database, There's a leopard database, experimental database. You can go and like ask for the data, but a lot of them don't have an API. They don't have a way to, you have to like click a button and click basalts and then Hawaiian basalts. And then they go, here's a spreadsheet. And then you can do stuff, but you can't like write code to be like, to ask, you know? And so I think they're suffering from the same problem. And unfortunately, there's another layer there of, okay, well, these data, can we even compare these data sets because they're done on experiments and that person used this apparatus and that person used this apparatus. So a whole other can of worms. So maybe it's the same problem. So I don't know, is the answer to your question. It's complicated, yeah.
Hi, I appreciated your idea of putting the gases into the real-time monitoring volcano observatories. Full disclosure, I was postdoc at AVO, so
Nice.
I've seen behind the scenes of like the politics and the arguments that go on.
Yeah.
So this is more of maybe a people question than a data question, but
Sure.
like, how would you go about like convincing, in particular, folks like the USGS that like, you know, the data you're giving them is the correct
It's the
data?
correct data.
Yeah.
Yeah, that's a good question. It's a very good question. I mean, I will wax poetic. The real answer is I don't know. You know, I'm sure I'm not a seismologist, but I would imagine that those discussions happen about the seismic data too. I think there are enough people within the USGS community that do volcanic gas stuff that you have like a sort of pre-built-in audience. And because they're so prolific, the instruments to measure volcanic gas is already there. Like all of these volcanoes are outfitted with it. It's like it feels like a low-hanging fruit. And even if you say, okay, you don't need to base your policy decisions on it, even just getting in the door, I feel like it's doable with the USGS. And I feel like there is a lot of politics there, but I think there's also like a lot of people who want to build these tools, and that's like their passion. So I think doable. I'll let you know when I hit a wall trying to make it happen. But if you have any advice, you'll let me know from that side. Yeah. Debatable. All right.
Let's give our speaker one last round of applause.
Okay.